Alright everyone, welcome to the last MathBytes video in our series on how to do vector analysis in intro physics. In this video, we'll go over the kind of last skill that I think you all will need, which is doing vector arithmetic without having to use the graphical representations. That way later on, when you're doing like homework problems, when you're studying forces or momentum, or any of the other vector quantities, you can compute exact vectors without having to draw pictures and take precise measurements. For those of you who know what's going on and just kind of want the formulas, you can go ahead and skip to the last chapter where I summarize all the formulas for addition, subtraction, and scalar multiplication. But if you want to understand why those formulas work, I will encourage you to stick around for the entire video and we'll do kind of a pretty deep dive on why they work the way they do. Okay, so like we've talked about in previous videos, right, there's kind of two main ways that we'll represent vectors in physics. The first one is the polar representation, in which we directly give the magnitude and angle. And so in this representation, right, we give an ordered pair of r comma theta, where this first value is the magnitude of the vector, and we just basically directly tell what the length is. We also need to give the direction, right, since vectors are defined by both a magnitude and a direction. And so we usually give that in the form of an angle relative to the positive x-axis. So for this vector, kind of on the right-hand side here, vector r, the polar representation is basically telling us how long the vector is, and that way we can construct the full vector. And the other representation we'll use is the rectangular representation, in which we just give the components in the x and y directions. For this vector, for example, that might mean telling someone how far this vector extends horizontally, and we'll call this the x component, rx, and telling the person how far this vector extends vertically, and that's the y component, ry, right? And so basically we give them kind of the ingredients so that they can reproduce this vector by themselves. As we saw in previous MathBytes videos, right, it turns out there's really no obvious way to add vectors in polar coordinates, but as we'll see in this video, the rules for vector arithmetic are much easier in rectangular coordinates. Since we covered how to convert between rectangular and polar in the last video, I'm just going to assume that anytime you need to do this, you'll be able to convert into rectangular coordinates, and so we'll keep things simple and just assume every single vector in this video is handed to us in rectangular coordinates. Or in other words, we have all the components right from the get-go. Okay, let's hop in with vector addition. Before we start doing some picture stuff, I want to remind you of two key ideas that are related to vector addition. The first key idea is that vector addition is kind of like following sequential directions. In other words, right, when we add two vectors, so if I have like a vector u and a vector v, well, the resultant vector from adding these two vectors is the one that I get if I just follow these two arrows to the end, right? It's like where I start and where I end up, like this. Kind of like if you were following directions on like a treasure map or something like that. The other key idea is that the sign of the vector component will tell us which direction that component goes in, right? This key point kind of comes from the idea that all vector components are given in terms of a vector basis. And the vector basis that we use for the most part is the standard Cartesian one, in which positive components either point to the right or upwards, depending on if they're x or y components, and negative components either point leftwards or downwards, depending on, once again, whether we're talking about the vertical or horizontal, the x or y. Okay, good. And so this second idea gives us a really useful intuition for vector addition. We can basically freely add vector components because the negative components mean go left or go down, and the positive components mean go right or go up. So we kind of have this like nice clean mapping between directions and signs. So let's consider a case where we have two vectors that are just kind of purely horizontal. The vector u has an x component of 5 centimeters, and vector v has an x component of minus 3 centimeters, and neither of these vectors has any y component, so they just kind of lie along the x-axis. And so let's say that my goal is to compute the addition between u and v, and we'll call the resultant vector r, right? And what I would like to do is be able to write down the components rx and ry, just in terms of the components of u and v, the two vectors that I'm adding together. And so what I'm going to do is first compute the sum graphically. And so let's start by drawing vector u, right? Because that's the first one in the sum. And vector u is going to look something like this. We know it extends 5 centimeters to the right because it has an x component of plus 5. Then if I want to add a vector v to u, right, I need to start v where u ended. So that's going to be right here at the 5 centimeter mark. And this vector extends 3 centimeters in the negative x direction. In other words, to the left. And so then if I want to draw my resultant vector r, right, I know that the resultant vector is going to start where my first vector started, right here at the origin, and it's going to end where my second vector ended, which is right here at the end of v at the 2 centimeter mark. And so then that means my final vector r looks like that. And so from this picture, right, we can tell that the x component of r, rx, is really just 2 centimeters. And ry is 0 centimeters. And so going back to the idea that vector addition is just following sequential directions, right, we can see how this came up. We started by going 5 centimeters to the right, and so we can have this plus 5 centimeters here first. And then we followed the vector v and saw that vector v was telling us to go 3 centimeters to the left. And so we can subtract 3 centimeters, and this is what gives us our 2 centimeter resultant. And so we see here how kind of the signs play nicely, right? They really match on to our intuition that positive numbers mean go right and negative numbers mean go left. We can see this graphically over here on the left-hand side as well. And so it seems to be the case here that generally when we have two vectors being added, ux, uy, and vx, vy, we can compute the components of the resultant vector by adding up the x components individually and adding up the y components individually. This idea is called component-wise addition because we're adding the components kind of separately from each other. Okay, so I've given you vectors here that are just one-dimensional, right? They only point to the right or to the left. So let's just make sure this kind of component-wise scheme makes sense for when we have vectors that have non-zero components in both directions. So here are two new vectors. Vector u now has x and y components, and vector v has non-zero x and y components. And once again, let's try to compute the resultant vector r equals u plus v, right? And so once again, I'm going to start things off by doing this graphically. And so vector u has an x component of 3 centimeters, even though that might look like a 2, and a y component of 4 centimeters. So vector u is going to start from the origin and point to about here. And so if I want to add vector v to vector u, well then what I'm going to do is start where vector u ends, and I'm going to draw vector v at the end of that. So it goes 2 centimeters to the left and 1 up. So I should try to aim to draw it like that. Perfect. Okay, cool. So let's draw out the resultant sum of these two vectors, and that's going to point from here to about here. And what I'm going to do is demonstrate that this component-wise addition thing still works by drawing the projection of the x and y components onto their respective axes. So what I mean is let's start with the x components. The x component of this red vector is going to be the component that points along the x direction like this, right? It extends 3 centimeters to the right. And then what I can do is overlay the x component of the blue vector on top of that. And so I can start at the end here, and we know the blue vector extends 2 centimeters to the left. And so that's what our x component looks like for vector v, right? And what I notice is that that exactly coincides with the x component of the resultant vector. So it seems to be the case that the sum of the components in the x direction still exactly just gives us the x component of the resultant combined vector. If we do the same exercise with the y components, I can see that the y component of my red vector looks like this, right? And the y component of my blue vector looks like this. And once again, this exactly coincides with the projection of my resultant vector on the y-axis. And so because both of these purple resultant components are really just the sums of the individual kind of x and y components of u and v, we can be pretty sure that our formula from the last page works generally speaking. In other words, rx, the x component of the resultant vector, really is just the sum of ux and vx, and ry is just the sum of uy and vy. And this all really stems from the idea that algebraic vector addition is just following sequential direction. Okay, cool. So I think that's probably good for addition. Let's move on to scalar multiplication. Okay, so first, let's review what scalar multiplication does. So remember from before, scalar multiplication makes a vector longer or shorter without affecting the direction. So for example, given this vector u in black, if we wanted to scalar multiply this vector by 2, well, what that really is a vector in the same direction, but it's twice as long. So I can illustrate that by kind of drawing two u vectors lined up. And my vector 2u is going to be the same direction as the original vector u, but twice as long. We can also scalar multiply by fractions or numbers that aren't exactly integers, right? And so something like 1/2 u would be a vector that is in the same direction as u, but it's only half as long. So vector 1/2 u might look something like that. Okay, so now that we've reviewed what scalar multiplication does, let's think about how to do vector or scalar multiplication, algebraically. And so the way that I like to think about scalar multiplication is through a geometric argument. And so one thing we saw in the last video, right, is that vectors kind of form the hypotenuse of a right triangle and the x and y components form the legs. So given this vector u, in which we've given you the x and y components, right, we can kind of draw a little diagram that reminds us that vector u might look like this with components that form a right triangle like this, and I'll label these components as well. Then we can also recognize that if I scalar multiply this vector u, right, it's going to give me a new vector in the same direction, but is a little bit different in length. And so for this problem, let's assume that our scalar here, this lowercase n, is less than 1. In other words, it's going to make the vector a little bit shorter than it was before. And so our vector n times u, let me draw that a little better. N times u might look something like this. And remember, our goal is to figure out what the components of this new vector are. And so I'll label these u star y and u star x to remind us that they're a little bit different than our original vector u, right? And so what I can recognize here is that these are similar triangles, right? We know that because this is the same vector and its direction hasn't changed, these two angles are the same. We also know that these x and y components of the new vector are still at right angles, right? And now that we know that two of the angles of the triangle are the same, then the third kind of corresponding pair also must be the same. And so that way we can tell that these are similar triangles. And if we remember back to geometry, right, whenever you have two triangles that are similar, the corresponding sides are also proportional by the same amount. What I mean is if the hypotenuse of the triangle on the right is like half as big as the one on the left, well then the entire triangle is half as big. And so the legs are also off by the same amount. That means that we can directly write down that whatever proportion the hypotenuses are different by, well then the components must also be off by that same proportion. In other words, u star y is just n times uy, and u star x is n times ux, like so. And so we can summarize scalar multiplication with a formula like this. Consider multiplying a vector u by some scalar n. If we write out the component form using our nice color-coded scheme, this is going to be n times ux comma uy. And like we saw from our kind of triangles argument, right? What happens is that this gives you a new vector with components that are multiplied by the same scalar, because this scalar affects all three kind of sides of this triangle exactly proportionally. So there's one small wrinkle we should also cover. What if n is a negative number, right? Does this work for if n is negative? So let's do one more quick exercise. Remember that a negative scalar causes the direction of a vector to flip, right? So if vector u is this vector I've drawn in black here, well then minus u has the exact same length, but goes in the opposite direction as our original one. If we have a negative scalar that's not exactly equal to 1, right, then we flip the vector first and then just do the same thing where we scale the length based on the kind of magnitude of that scalar. So in this case, right, minus 2u is the same as negative u twice. And so minus 2u is going to look something like that. And so let's make sure then that our scalar multiplication rule also works if our scalar is negative. So I've written down the formula that we came up with on the other page here. I'll put a box around it just to kind of highlight it a little bit. And we want to check to make sure what happens if we apply a negative scalar here. So what I'm going to do is draw a vector, and I'll give it a negative x component. We can see the x component points to the left, and it has a positive y component, right? So let's call this ux and uy. Okay, now let's try to compute the vector negative u, right? So if this is vector u, we know that negative u has the same length, but is in the opposite direction as our original vector. Then what I can do is take a look at the components here, right? So because vector u had an x component that was pointing to the left, then the vector negative u looks like it now has a component that points to the right, right? Similarly, if I look at the vertical components, the y component of vector u originally pointed upwards, but now this one has the vector going downwards. Just to make things extra clear, I can kind of label these minus ux and minus uy, but we can see that it's certainly true that applying a negative sign here just caused the directions of the individual components to flip. And that's what gives us our kind of final vector that points in exactly the opposite direction. Multiplying the vector by a negative number is identical to multiplying the components also by a negative number. Okay, let's move on to our final vector arithmetic operation, which is going to be vector subtraction. And so remember, the way that we formulated vector subtraction in our earlier video was that vector subtraction is the same thing as adding an opposite vector, right? So if I have a vector subtraction problem like vector u minus vector v, well, that's equivalent to vector u plus negative vector v. And just so we can see this in action once again, if I want to do vector u minus vector v here, I can start by drawing vector u. And I need to write down the flipped version of vector v, right? So if this is vector u, and v points this way, well then minus vector v must point this way. And so my resultant vector looks like that guy, right? And so when it comes to the algebraic version of this, well, we just covered how to do scalar multiplication, right? So we know what to do with vector components when we multiply by -1. We also know how to do vector addition here, right? Vector addition is just component-wise. So we can actually combine the algebraic formulas we came up with in the last two sections to figure out what vector subtraction looks like. So let's start by writing out vector subtraction in component form. So we have ux and uy, and I'm going to color code these a little bit differently just so that all the u components are red and all the v components are blue to make this a little more clear. Vector v looks like vx and vy. And if I rewrite this as an addition problem, or in other words, if I kind of rewrite this as adding a negative vector, then this is ux, uy plus negative vx, vy. And we know that when we multiply vy by a negative scalar, right, what that's going to do is kind of distribute this negative sign into both of the components. And so this now looks like ux, uy plus negative vx, negative vy. And so now we've reduced this to a vector addition problem. And we know that to do vector addition, we just do the addition component-wise. And our resultant then for vector u minus vector v is going to look like ux minus vx and uy minus vy. Just like vector addition is component-wise addition, right? What we find is that vector subtraction is really just component-wise subtraction. This isn't too surprising since addition and subtraction really, like, even when we do it with scalars, are kind of the same operation, right? So it makes sense that the same component-wise rule applies for both vector addition and vector subtraction. Okay, so that was all three of the operations I wanted to go over, and I know that was a lot of math and geometry, and practically you guys might just want the formulas so that you can do your big pile of homework problems. So let's move on to summarizing our formulas here. So here's all the formulas for addition, subtraction, and scalar multiplication, and let's go through them kind of one by one. So for vector addition, right, given two vectors u and v, we wanted to find the components of the resultant vector rx and ry. What we found when we drew our vectors and did the graphical sum was that we can compute the total resultant Rx by just adding the x components of the individual vectors ux and vx. And similarly, we found that the y component was just the sum of the individual y components uy and vy. For scalar multiplication, what we found out is that whenever you take a vector and multiply the vector's length by some scalar, that has the effect of multiplying the components as well by the same scalar. And we saw why that had to be the case using our kind of similar triangles argument, right? And finally, for vector subtraction, we used kind of both of the ideas we came up with for vector addition and multiplication to find out that vector subtraction is also done completely component-wise. In other words, when you subtract two vectors u and v, then the resultant vector just has an x component that's given by ux minus vx, like the subtraction between, the x components, and uy minus vy. Okay, cool. So those are the summaries for kind of the formulas we've developed here. It's not strictly necessary that you fully understand why these formulas work, but I think it can help if you need to basically do some emergency reasoning on a test. So, worth studying, but at the end of the day, just make sure you know how to use these formulas. All right, that's really all I have for this video. I hope this MathBytes series helped you feel a lot more confident about vectors in physics. Vector arithmetic comes up a lot, and so I think any time that you spend just getting familiar and practicing these concepts is going to be really, really well worth it as you go through the intro physics courses. Also, if you have any lingering questions about anything in this series, please feel free to leave those down in the comment section below and I'll try to answer them. And as per usual, please don't forget to like and subscribe for more free physics problem solving tips and tricks. This has been Physics Tutoring Quantized.